Hello everybody. We're getting ready to do lesson 9.3 part 3 of your classwork, pre-calculus math today. If you need questions or materials, answers to your questions, animated PowerPoint math video at AOL.com. Today's lesson will have 16 points that will go into your notebook guide and then 40 points on your classwork sheet. So I have that ready. Students, put your name, date, period. If you're an onliner or a homeschooler, put your due date here. And today's bell work, factor this polynomial completely. Factor this one completely here, students. Teachers, give your students about 4 minutes to do this. Check back in 4 minutes. Pause your video. Okay, everybody, welcome back for your solutions of today's bell work. 16 x cubed plus 54 factored completely. We're going to factor out a 2 here, 8x cubed plus 27. We can factor out a 2x plus 3, and then we have a quadratic here, 4x squared minus 6x plus 9 for 109. And then down here, 4 minus x plus 4x squared minus x cubed. We're going to factor out a 4 minus x out of this, 4 minus x plus, and then x squared factored out of 4x squared minus x cubed be 4 minus x. So we have two 4 minus x's here. And then we can just factor again 4 minus x times x squared plus 1 from this, extrapolating from that. On into our lesson today. Another interesting application of conic sections involves the orbits of comets in our solar system. Of the 610 comets identified prior to 1970, 245 have elliptical orbits, 295 have parabolic orbits, and 70 have hyperbolic orbits. The center of the sun is a focus of each of these orbits, and each orbit has a vertex at the point where the comet is closest to the sun as shown. So here's the sun. So our sun again is a focus of these orbits here, and it's interesting to see how the sun affects all these orbits of these comets. Undoubtedly, there are many comets with parabolic or hyperbolic orbits that have not been identified. You get to see such comets only once. Comets with elliptical orbits, such as Halley's Comet, are the only ones that remain in our solar system. That's interesting there. Halley stays in our solar system. Okay, so if P is the distance between the vertex and the focus in meters, and V is the velocity of the comet at the vertex in meters per second, then the type of orbit is determined as follows. So our ellipse will be V is less than radical 2gm divided by P. And then a parabola would be V would equal radical 2gm divided by P. And then a hyperbola, V would equal, or rather V would be greater than radical 2gm divided by P. So there's definitely a situation here of a parabola V equals that. Ellipse V is less than, and a hyperbola V is greater than 2gm divided by P. In each of the above, M is approximately 1.989 times 10 to the 30 kilograms, the mass of the sun, and G equals or approximates 6.67 times 10 to the negative 11th cubic meter per kilogram second squared, the universal gravitational constant. So that's kind of cool to know this number. Universal gravitational constant. So you're getting some astronomy in here. General equations of conics. Classifying a conic from its general equation. So the graph of ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 is one of the following. A circle is A would equal C here, so A would equal C. A cannot equal 0. And then the parabola AC equals 0. A equals 0 or C equals 0, but not both. And then an ellipse will be AC is greater than 0. A and C have like signs. So classifying a conic from its general equation, this is a pretty nice little equation here. And then you can tell the different kind of conic from what these values are down here. And then a hyperbola will be AC is less than 0. A and C have unlike signs, so a hyperbola is definitely a different kind of conic. That's so classifying conics from general equations. Classify the graph of each equation. A will be 4x squared minus 9x plus y minus 5. So what would that be, class? For the equation 4x squared minus 9x plus y minus 5 equals 0, you have for AC will be 4 times 0 in this case. 4, there is no C in here, is there? 4 times 0 would equal 0, so it's a parabola. So the graph is a parabola for this one here. And then for B, 4x squared minus y squared plus ax minus 6y plus 4 equals 0. So this equation here, you have AC is 4 times negative 1. In this case here, AC is negative 1. So 4 times negative 1 is less than 0, so that makes it a hyperbola in this situation here. So the graph is a hyperbola. And then for C, 2x squared plus 4y squared minus 4x plus 12y equals 0. For that one, for the equation, you have AC equals 2 times 4. So 2 times 4 is greater than 0, so it would be an ellipse. So that would be a quick way that you could tell what these are expressions of just by looking at them. And then D, 2x squared plus 2y squared minus 8x plus 12y plus 2 equals 0. For the equation, for this equation, you have A equals C, which equals 2. So A equals C. So A equals C here. So wait a minute, A equals C. So A equals C equals 2 equals is a circle. A equals C equals a circle. So the graph is a circle in this situation here. Okay. So starting into this guided practice here, classify the graph of the equation as a circle, a parabola, an ellipse, or a hyperbola. So this equation here, this is our guided practice. Students, this is yours down here. Finish that one on your own. But we're going to do this one up here. So from this equation here, what kind of conic would it be? It'd be 9x plus 4y minus 18x plus 16y minus 119 equals 0. A equals 9. And then our C equals 4 here. So AC equals 36, which is greater than 0. So we know it's an ellipse just by looking at it. Okay, moving on. Rotation. In your notebook, page 7, you've learned that the equation of a conic with axes parallel to one of the coordinate axes has a standard form that can be written in a general form, ax squared plus 3y squared plus dx plus 3y plus f equals 0. So this would be a horizontal or vertical axis in this situation here. You will now study the equations of conics whose axes are rotated so that they are not parallel to either the x-axis or the y-axis. The general equation for such conics contains an xy term. So for an xy term, to eliminate this xy term, you can use a procedure called the rotation of axes. The objective is to rotate the x and y axes until they are parallel to the axes of the conic. The rotated axes are denoted as x prime axes and the y prime axes as shown. So here our y prime would be here, and then our x prime would be here. Here I have a differentiation here of theta. After the rotation, the equation of the conic in the new x prime y prime plane will have the form of a prime x prime squared plus c prime y prime squared plus d prime x prime plus e prime y prime plus f prime equals 0. So this will be a rotation of your axes for the that will adjust to the parallel to the axes of the conic. We can move our other axes to that. Because this equation has no xy term, you can obtain a standard form completing the square. The following theorem identifies how much to rotate the axes to eliminate the xy term, and also the equations for determining the new coefficients a prime, c prime, d prime, e prime, and f prime. Okay, so the rotation of axes to eliminate an xy term. The general second degree equation ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 can be rewritten as a prime x prime squared plus c prime y prime squared plus d prime x prime plus e prime y prime plus f prime equals 0. So that would be your new general form there. By rotating the coordinate axes through an angle theta, where cotan 2 theta would equal a minus c over b. So now we can turn it into a trigonometric kind of situation. The coefficients of the new equation are obtained by making the substitutions x equals x prime cosine theta minus y prime sine theta, and y would equal x prime sine theta plus y prime cosine theta. Note that the substitutions x equals x prime cosine theta minus y prime sine theta and y equals x prime sine theta plus y prime cosine theta were developed to eliminate the x prime y prime term in the rotated system. You can use this to check your work. In other words, when your final equation contains an x prime y prime term, you know that you have made a mistake. Okay, let's try one now. Example 7, rotation of axes for a hyperbola. Rotate the axes to eliminate the xy term in the equation. So we have xy minus 1 equals 0. Then write the equation in standard form and sketch its graph. So because a equals 0, b equals 1, and c equals 0, you have cotan theta equals, or rather cotan 2 theta equals a minus c over b equals 0, which implies that 2 theta equals pi over 2, or theta equals pi over 4. The equation in the x prime y prime system is obtained by making the substitutions here. B equals 1, remember? Up here, b equals 1 down here. So x equals x prime cosine pi over 4 minus y prime sine pi over 4 would equal x prime y over square root of 2 minus y prime multiplied by 1 over square root of 2. So x prime minus y prime over radical 2, and y equals x prime sine pi over 4 plus y prime cosine pi over 4, emulating this situation up here. And you come up with x prime multiplied by y over radical 2 plus y prime 1 over radical 2 equals x prime plus y prime The equation in the x prime, y prime system is obtained by substituting these expressions into the equation xy minus 1 equals 0. So when we do that, we come up with this here. For xy, we have x prime minus y prime over radical 2 multiplied by quantity x prime plus y prime over radical 2 minus 1 equals 0. Then when we do that, when we square these out, we get x prime squared minus y prime squared minus 1 equals 0. Then when we do this, when we write this in standard form, this is what we have. X prime squared over radical 2 squared minus y prime squared over radical 2 squared equals 1. In the x prime, y prime system, this is a hyperbola centered at the origin. So here's our center here, with vertices at plus or minus radical 2, 0. So here we are, radical plus or minus 2, 0, because this is our new x-axis here, say, or x prime axis will be right here, and as shown. So here it is shown here. To find the coordinates of the vertices in the xy system, substitute the coordinates plus or minus radical 2, 0 into the equations. X equals x prime minus y prime over radical 2, and y equals x prime plus y prime over radical 2. And then when we do that, we have a situation here that yields the vertices at 1, 1. This would be 1, 1 here, 1, 1, using our standard vertex identification, and then negative 1 for this vertex here. Note also that the asymptotes of the hyperbola have equations of y prime would equal plus or minus x prime, which corresponds to the original x and y axes. So the vertices would be in the x prime, y prime system will be radical 2, 0 and negative radical 2, 0. So that would be your vertices here. A positive radical 2, 0, then negative radical 2, 0. And then in the xy system, it would be 1, 1, and then negative 1, negative 1. So let's try one now. Rotate the axes to eliminate the xy term in the equation. Then write the equation in standard form. Sketch the graph of the resulting equation showing both sets of axes. So we have xy plus 1 equals 0. So what we need to do is we have our cotan 2 theta equals a minus c over b equals 0. And then when we substitute in our values, we have 2 theta equals pi over 2. Which equals theta would equal pi over 4. And then down here for x, it would equal x prime cosine pi over 4 minus y prime sine pi over 4 equals x prime radical 2 over 2, which corresponds to pi over 4 minus y prime sine of pi over 4 would be radical 2 over 2. Which will equal our x prime minus y prime over radical 2. And then our y, when we go through this litany here, will become x prime plus y prime over radical 2. And this is all for xy plus 1. So these are your solutions here. And then sketch the graph. Then write the equation in standard form. So these are our standard forms now for this xy term in the equation. And then sketching the graph, students, I'm going to let you do that yourself. Sketch the graph and cite your classwork notes to sketch that graph. And that is, oh, look at that. I got your solutions. If you need solution PowerPoints, email me for those. animatedpowerpointmathvideo@aol.com. And that is 9.3 part 3 for pre-calculus math. If you need full course suites of solution PowerPoints, quizzes, tests, homework sheets, note-taking guides, and classwork sheets. Animated PowerPoint Math Video, AOL.com. Thank you very much.